Alright, so we've got a new project that we're starting. It's going to be a whole lot shorter than the 8-bit CPU project, I can tell you that right now, but it's going to be a hexadecimal clock. Now what we're going to do today in this video is sort of just outline what this clock is and the major parts that we need to construct. I've already started constructing it basically. Now of course with a normal clock you need 4 displays, right? Your maximum time is going to be 1259. So you're going to need a display for each of these numbers, assuming that you don't want a display for this colon, which I don't. Now with 2 displays, things get a little tricky. Now some of you can already be piecing this together why it's called a hexadecimal clock, and that's because with hexadecimal, you can use 1 digit to correspond to the numbers 0 through 15. And the way you do this with 1 digit is you use the digits 0 through 9 to correspond to 0 through 9, and then after that you use A through F, which is going to correspond to 10 through 15. So that means with 1 digit you can actually show the numbers 0 through 15. And all these numbers and letters correspond to their own shape on this 7-segment display, so we have no problem there. Now technically with a 7-segment display you have 7 segments, so that means you have 7 possible options, and you have 2 options for each segment, meaning that it can either be off or on, so you get 2 to the power of 7, which is equivalent to 120. So that means with 1 segment display, you could actually show 120 possible different symbols. Now, figuring this to time, assigning each of these 120 values to time, means that you could have 120 different times with 1 segment display. Now factor out the 12 hours, right? So 120 divided by 12, you get 10. So that means you get 10 possible options for each hour, which roughly equates to this LED changing, this symbol on the display changing roughly every 6 minutes, because we're dividing 60 minutes by 10 possible options. Now that's not bad. Being able to tell time up into about every 6th minute with only 1 display is pretty good. You know, considering the amount of information that you're looking at, we're getting a pretty accurate time representation. Now the harm in this is that of course you have to memorize 120 different symbols. Now I don't know about you, but that seems like quite a pain. So using 1 symbol is really not the best option. So we can go ahead and use 2 displays, which is good because I have 2 displays, and we can show 0, and 1 display can correspond to the hours and 1 display can correspond to the minutes. Now this of course means that for the minutes, now for the hours we have no problem because we have 15 possible digits to represent 12 different hours, so we're okay there. Now for the minutes, of course, we only have 15 possible characters to represent 60 minutes, so 60 divided by 15 different symbols means that we get a symbol about once every 4 minutes. So that's the accuracy with which this clock will be able to tell. It'll tell you within 4 minutes what the time is. Now that's not bad at all, and for me as someone who's pretty much always late to everything by at least 4 minutes, being able to tell time up until 4 minutes is pretty good enough for me. What I decided to do for the discussing the development of this project is a top-down development, because we've already talked about the displays, it just makes sense. Also because this project is quite a bit easier than an 8-bit CPU, we don't have to talk about each individual component and then talk about putting those components together. We can instead talk about what we want the end game to be. Now for a CPU, talking about the end game, we want to be able to calculate numbers automatically, doesn't really clue you in at all to what we need to be doing on the component level. But with something as simple as an LED clock, well, it's not that bad. We're going to need something that can drive these LEDs, and it needs to be able to tell the difference between, ultimately, if we choose to have 12 different options for the hours, and 15 different options for the minutes, you can see that we get 180 different options. That means we need something that's going to be able to take these 180 options and output a specific character onto these displays, a different symbol onto these displays. Now the easiest way to do this is with an EEPROM. Now we've used EEPROMs before in the 8-bit CPU and they're pretty wonderful, The joy of them is that we can plug them into our computer and program all these 180 different options, and what they'll do is they'll connect to these LED displays and drive them corresponding to the 180 options. So, you can take a log 2 of 180, and that'll give you something that is greater than 7, meaning that we're going to need more than 7 bits to tell 180 different options, and that makes sense because 2 to the 7 is 120. So we're going to need 8 bits, which is 200. Sorry, that's not 200. That's 128. 256. 2 to the 8 is 256. Now we only need 180 of these 256, but we're still going to need 8 bits nonetheless. So for starters, we're going to have 8 bits travel into this EEPROM. Now these 8 bits will tell the EEPROM what the time is that it needs to be displaying on the clock. Now for those of you who remember from the 8-bit CPU, the EEPROM only has enough outputs that it can only drive a single display at a time, but we've got 2 displays. So what we can do is use a 9th bit to drive the EEPROM, and this will tell it either 1 or 0, where 1 might correspond to the hours digit and 0 might correspond to the minutes digit, and this will just say, alright, take the time, and if it's a 1, output the hours, and if it's a 0, output the minutes, and we'll just flash through these really quickly so that this way the value on the displays will change really quickly, and people really won't be able to tell that we're only displaying one number at a time. It'll just look like we're displaying both of them. So the next question is, where do these 8 bits come from? Now it's time, so that means that as each minute passes, we're just going to be adding 1 minute plus 1 minute plus 1 minute plus 1 minute, and if we total these up, we'll get whatever time we're at in minutes. Something that just keeps adding on a uniform clock is just a counter. And because we're talking about binary, we're going to use a binary counter. So what we can do is have a counter. So we can have a counter, and we can have a clock signal, and have that go into the counter. And this counter is going to have 8 bits come out of it, and the value on the counter is just going to keep increasing by 1 for every clock cycle of the clock signal. Now if we set the clock signal to be 1 minute, meaning that the period length between the peaks is 1 minute, that means that the counter is going to increase by 1 every single minute. Now because our resolution for this clock is actually going to be 4 minutes, we only have to change the value every 4 minutes, we could technically at a maximum set this clock signal that goes into the counter to be 4 minutes, meaning that 4 minutes goes into the counter, and once every 4 minutes the value changes on the counter, increases by 1, and these go together. So this value outside the counter goes into the EEPROM, and then we can just program the EEPROM to correspond to whatever value the counter is, means this value on the clock. Simple enough, right? Now, how do we create this primary clock signal? Well, we already know how to create a clock. We did that in the 8-bit CPU video. So we can just use a simple 555 circuit, and this will use the charging and discharging of a capacitor to create a clock signal. And this clock signal would go into our counter, which will then go into our EEPROM. So we've got a pretty simple layout that we've already figured out here. There's nothing else that we really need for this circuit. These are the main components, really. I mean, of course, to change this value on the EEPROM, because we're going to need a 9th bit, so we're going to need another clock signal which is of a very high frequency, so this way the EEPROM changes values very quickly. But we'll worry about that in a later section. But right now we can just worry about these 8 primary bits which translate the information. You could go ahead and create a 555 timer that has a period length of 4 minutes pretty easily. There's a formula in the data sheet of all 555 timers that tells you exactly if you use this resistor and this capacitor value, it'll give you a period length of this amount of time, and you can go ahead and plug in your numbers and figure out exactly what component values you need. Now technically you don't need to create a clock signal of 4 minutes. Technically you could do any sort of multiple of 4 minutes. So you could do 2 minutes or 1 minute or 30 seconds or 15 seconds. You could do really any amount of time. It just needs to, some way you need to have a stable amount of time which you're going to base this clock on. Now the easiest thing is to do 4 minutes, because then you can just have the 555 timer go straight into the counter. Now, to do a clock signal in 4 minutes, you need either a really large capacitor or a really large resistor, neither of which I actually have on storage, so I'm not going to do 4 minutes. Instead, what I've chosen to do is 1 minute. So we have this 555 timer, and through some use of resistors and capacitors, I am creating a clock signal, a stable clock signal, a whole hell of a lot looking stabler than that, but it is going to have a period length of 1 minute. Now, I could also do 30 seconds, or I could do 15 seconds. It doesn't really matter. But what we just need to do is pass this through a counter, or a program counter, which is going to divide this clock signal by 2 each time it counts. Counting, you can remember in binary, is very cool, because if we say we have the first digit here, second, third, and the first digit is going along, well, then the second digit, and we can label these 0, 1, 0, 1. Well, for each alternate of this, so let's just say it starts at 0, 0, and then it's going to change here. So you can see we get 0, 0, then 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Now you can see, just looking at the first 2 digits, how this counting is going to work, right? So first we're going to get 0, 0, then we're going to get 0, 1, and then we're going to get 1, 0, and 1, 1, and then it's going to carry on to the next bit. But you can see that we're actually counting here, right? You can see that we're actually counting, right? So 0, 0, 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. So we're counting along. But you can also see that looking at the clock signals, treating each of these digits like clocks, the period length for this second digit is exactly twice as long as the period length for the first digit. Now likewise, if we look at the third digit, we can see for every 2 changes in this, we're going to get a single change in the third digit. So we get 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. Now we can take a look at the counting. So we start at 0, 0, 0, 0, 0, then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and so on and so forth, right? But looking at treating the third digit as a clock signal, you can see that the period length is exactly 4 times as long as the first digit. So meaning, if we set the first digit to be equal to our 1 minute period length, well then the third one, then if we set so if we plug our 1 minute clock signal into a counter, then we take a look at the third digit, we're going to be outputting a clock signal which has a period length of 4 minutes. So just like that, we've created the 4 minute signal that we need for our EEPROM based off of a 1 minute 555 timer. And then this 4 minute signal is going to go into the counter yet again, and we're going to be taking the preceding next 8 bits, and those are going to correspond to our time signals for the EEPROM. This is the basic layout for our hexadecimal clock. So now I think it's time to take a look at the circuit, and the first thing to take a look at is a clock circuit. Now this is a 555 timer. Now this is how the timer is going to, now this is the actual circuit diagram for our timer. Now the clock signal is going to appear at this point right here. This is where we're going to get our 1 minute clock signal. It's going to, the LED is going to be on for 30 seconds and then off for another 30 seconds, giving us a total period length of 1 minute. And you can see these are our resistance values, and we're charging and discharging our 47 microfarad capacitor through ultimately 840 kiloohms, and we're discharging through 830 kiloohms. We're all familiar with this circuit because we already built a clock for our 8-bit CPU, but it's just nice to take a look at the circuit diagram. Now you can go ahead and go on the data sheet and find the equation that says if you have this resistor and this capacitor, then you'll get a time period length of this. And usually what it tells you is how long the LED will be on for, meaning the half period length. And if you plug in these values, you'll actually get something like 27 seconds or so. You won't actually get 30 seconds. And the reason for this is because there's some sort of discrepancy in the values actually here. For example, this 47 so-called 47 microfarad capacitor, as marketed to me, as a 47 microfarad capacitor is not actually 47 microfarads. It is more than 47 microfarads, and that covers the discrepancy of the 27 seconds, of this 3-second discrepancy. So what I did is I was actually really confused because I found the values that would work for 30 seconds and found those components and put it in, and I was getting something that was larger than 30 seconds. So then I sort of just started to tinker with the resistance, started bringing the resistance down so that this way I could get close to 30 seconds, and it ended up working that these resistors with the capacitor that I had chosen was giving me 30 seconds. Now I've timed it. I've actually used a timer on my phone, and we've gotten consistent results of 30 seconds. So that we know these components work together. Now, ultimately, you're going to have to try your own components because it depends how badly marketed your components were. My components apparently were pretty badly marketed. 47 microfarads was a complete lie. So you're just going to have to end up finding a combination of components that works for you. So we can go ahead and take a look at this circuit. This is the 555 timer. I built a little bit more, but I'm covering that up with a piece of paper now because I don't want it to distract from what we're actually looking at. Now we can go ahead and actually plug this in so you can take a look at the timing yourself. Now we'll just wait for 1 cycle and then we'll go ahead and get a timer on the screen. Alright, so from there you can see that it was on for 30 seconds and off for 30 seconds. And it wasn't exact, but it was pretty darn close enough for what we need. What we talked about next for our timer is because that we have a 1-minute signal, we need to put it through a counter and get the 3rd digit to get a 4-minute signal out. And the way we do that is with this circuit. Alright, now these chips are the 4029 chips. These are binary counter chips. They also do decimal counting, but we're putting them in the binary function. You can see that here. Now on this portion is just a smaller version of the circuit that you guys just saw, which is the 555 timer. Now we can see that we have the clock signal of the 555 timer going to the clock pin of the 4029 counter, and we have on this first chip, we're cascading 2 of these chips together because each of them is only a 4-bit counter, and we're getting 2 of them to get an 8-bit counter. This of course is not going to give us our total outputs. Now these outputs are not going to be going directly into the EEPROM, and we'll explain that in a little bit, but right now this is just the counting portion. So the carry in for the first chip is obviously going to be tied to ground because we're not going to be carrying anything in. This is preset enable. This means that you can actually preset a value to this counter for it to start on. Now I don't want to use that functionality, so I've just tied that pin to ground. You can see power and ground for the chip. This is the up and down. So this means that if you have it on up, that means that it'll increment the clock on each rise of the clock signal. That means when the clock signal goes from 0 to 5 volts, that's when it'll increment. Or you can have it on the down function, meaning that when the clock signal goes from 5 volts to 0 volts, then it increments the clock. Now I just kept it in the up function, which means tie it to 5 volts. And this is the binary. Pin 9 is the binary or decimal functionality. So it has a decimal functionality to it, which means that it'll count in decimal. I'm not exactly sure how that works because I don't really care about it. So I've tied that pin high, meaning that it'll count in binary for me. And these are the outputs. Output 1, 2, 3, 4. And then it has a carry out. Now these pins, the carry in and carry out for these chips, are actually inverted, meaning that a high on the carry out corresponds to a 0 of value, and a low on the carry out corresponds to a 1 in value. But it doesn't really matter because it's going to get re-inverted when we tie the carry out to the carry in of the next chip, and that's how we cascade these 2 chips together. And then the clock signals are tied together, and we do the same sort of preset enable is automatically set to not being used, and binary functionality, and so on. And then we're going to be using Q1 through Q4 to give us our outputs 5 through 8, and then we can use the carry out pin to give us our output 9. I'm not sure if I want to use this because of course then we'll have to re-invert this signal when we tie it into the EEPROM. We don't actually have to do that. We could just set the 9th, we could just tell the EEPROM when we program it that the 9th bit is inverted and program it that way. But I think I might just not do that. Now the reason for this is because remember that the clock signal is 1 minute. So that means output 3 is our 4-minute signal. So that means we're going to need 8 bits past output 3. So output 3 is going to be our first, and then we need 7 more. So 1, 2, 3, 4, 5, 6, 7, and then we're going to need another 8th one, which means that we'd have to use 3 of these counters to ultimately get the 8th bit. But what we can do is create our own counter using a JK flip-flop, which we've done in the past. This is how we actually created our program counter for our 8-bit CPU. But we can go ahead and use a JK flip-flop. Each of these JK flip-flops, I believe, it has 2 JK flip-flops in each, meaning that we can split the signal by 4 across the JK flip-flop. So we can, what I'm thinking is we can use the JK flip-flop on pin 8, and that'll give us a, if we have the JK flip-flop clock signal tied to pin 8, that means that the 9th output would be on the JK flip-flop, as well as a 10th output on the JK flip-flop, which would give us our 7th and 8th bits that would go then into our EEPROM. Now I haven't actually done the JK flip-flop portion, but the circuit that you see here is actually already built, and that was what was covered by the piece of paper earlier. So you can see it here now. You can see we have these 2 chips here. Their clock signals are tied together. They have power and they have ground, and we've set all the pins that need to be set to ground, and so on and so forth. And this is the LED array for the outputs right now because we don't have an EEPROM. So we're just going to be checking the counting functionality on this circuit. So this is going to be the first, this corresponds to the first digit, and this will correspond to the 8th digit. Or is there 9? I think this is maybe the carry out, because we got 4 here and we got 5 here. So this is the carry out of the last one, our 9th bit. Now remember, this carry out is going to be inverted. I don't have a line that connects the clock to the clock, so we take the clock of our 555 timer and connect that to the input clock here of our 4029. Get power connected here. Now you can see it automatically starts at a random value, and the reason for that is because these registers already have something inside them, something random. Now, I don't want to have you guys sit here and wait for this to change every 30 seconds, because we'll be sitting here for a while before we get any real results. So I'm going to change out this 47 microfarad for a 4.7 microfarad, and that'll give us considerably faster. So now we can take a look, and you can see that we are actually counting through the values just like we were seeing earlier. Right. Now this is this being high actually means that it's a 0, remember that. But beyond that, just look at this beginning portion, it's counting just fine.